Let us continue with our 28th lecture in this course, looking at more advanced topics in process control. Just as a quick recap for the kinds of things that we have seen till now, this is a traditional feedback control loop, and we have discussed this in considerable detail till now. So, as a recap, this output measurement or output is going to be affected by both the input and the disturbance, and because it is linear, we said y of s is GPS us plus GDS ds. And then when we want this output to do what we want in terms of following a set point, or whenever there are disturbances we want the output to maintain its value. These are the two types of controllers that we talked about. The first one is called the servo control, the second one is the regulatory control. We close the loop, and the idea of closing the loop is looking at the difference between the set point and y, and then use that as an error signal to a controller, and that error signal the controller acts upon to give a input to the process. Now, if this error is 0, either the y set point did not change, but y changed because of ds, but it is now brought back to its original set point, or in the case of servo control, y set point itself changed and y is being dragged to get to the value of y set point whenever this error is 0. So, when this error is 0, I do not have to take any control action, but as long as there is an error, I keep taking control action to set it to 0. That way, this closed loop works for both the disturbance rejection and following set point. Now, clearly, at the beginning of this course, we started with a time domain understanding of the process and so on, and then we said if you use Laplace transforms, it becomes very easy to analyze these systems. So, that is the reason why we did Laplace transform, and once you do Laplace transform, closing the loop and analyzing this system just becomes a question of looking at algebraic manipulations. And we actually saw that for this closed loop, if you did simple algebraic manipulation by just writing down the equations, here u of s is c of s times e of s is y set point minus y. So, that is one equation here and here, and then y of s is simply gd of s d of s plus gp of s u of s, that is other equation. Now, what you can do is from these two equations you can write u of s as a function of the controller and set point, and then do some algebraic manipulation, and then you will basically derive in closed loop what happens, and we see that in closed loop I have this transfer function which is related to the servo control, and this transfer function which is related to the disturbance control. Now, after doing this, we looked at how you design a controller. We talked about a PID structure, P is proportional I integral d derivative, and then showed how the controller parameters could be tuned. And then we said tuning could be of two types. One is stability based, where you try to push the system in a closed loop with a P controller to as close to the stability limit as possible, and then basically back off from there to actually give the tuning parameters. The other approach we said was what is called a direct synthesis approach, which is to say, look, I have this closed loop function here, and ideally this should be 1, in which case ys will be just ys set point s, but that is simply not possible. So, I am going to use the simplest approximation to 1, which is something like 1 by tau closed loop s plus 1, and then once I know what I want this to be, I can back calculate the controller c of s, which is the idea of direct synthesis. Now, we talked about direct synthesis purely from the viewpoint of servo control. Now, all of these ideas are also directly translatable to the disturbance rejection also. Supposing you want to focus on disturbance rejection and then you want to have a particular form for the disturbance function model, you could use that and then say, okay, this is how I want my controller to be designed and so on. We focused on this closed loop, and I already showed you that whenever this works well, this also will work reasonably well. Remember the P controller example we talked about, where if you keep pushing the controller gain larger and larger, this will go closer and closer to 1 and this will go closer and closer to 0, which is what we want. This should go closer to 0 because we do not want any impact of disturbance on the output or minimize the impact of disturbance on the output in a closed loop. So, all of this we saw. After this was done, once we understood direct synthesis, then we said okay, let us look at what are the complicating dynamics that we can look at in terms of this GPS. Till that point we looked at simple first order systems, then second order system and so on, and you could expand this to third order, fourth order and all that. So, the order of the system is basically the order of the denominator polynomial. So, this is also something that we saw, and then once we understood all of this, then we said what type of complicating dynamics could be there in GP of S. We talked about 3 different types of complicating dynamics, which is one is the inverse response. The initial direction of change is different from the final value the output takes. We talked about time delay, where it takes certain amount of time before the action takes place, and the last thing was what happens if this GP itself is unstable, can I design controllers so that I make the closed loop stable. So, for each of these case now we have a good understanding of how the controller design should be done using a direct synthesis approach, and how do you get a PID controller after you do this direct synthesis approach. So, all of this we have seen. Okay. Now, as we go forward in this, we are going to be reliant on a model more and more, which is a point that I already made, and you could see for the first time in time delay systems you actually use a model while computing the input. So, we are going to explicitly use the model in controller computations also. That is one thing we are going to see. The other thing that I would like to show you in the next few lectures is to see what are the basic modifications that can be done to this loop itself in terms of adding more elements in the loop that will make control better. So, now that we have seen for this basic loop all kinds of complications and how to address those complications, we are comfortable with that. Now, is there a way in which we can think about adding more elements in the loop in some cases for some reasons that will make it better from a control viewpoint? That is the kind of thing that we are going to talk about. So, in the next few lectures I am going to first start with what is called cascade control, which is kind of modifying this loop a little bit more so that you can do control better, and I will explain a situation where cascade control will be very useful. I will follow that up with what call as a feed forward feedback control, again making some modifications to this block diagram so that you make the control better, and then I will show you multivariable case of expanding this loop, let us say to 2 variables at a time, 2 inputs and 2 outputs, and show you how one can generalize this idea of feed forward control to what is called as a decoupling control, and that idea I will explain with a 2 by 2 multivariable system. So, that will be the first time we will actually look at a 2 by 2 system in a block diagram form, more fleshed out block diagram form like this in this course, and you will see how this notion of feed forward control can be thought of as a forerunner for this decoupling controller, and look at expanding the single loop to let us say 2 loops at the same time which are interacting. How do you make them interact in ways that are favorable from a control viewpoint? And once we do that, then basically understanding control and learning control within this framework of feedback block diagram controller idea will be done. We will then go on to what is called model predictive control, where the controller itself is going to be directly computed based on model predictions, and there is going to be a notion of online optimization for computing the control moves. Okay, so that is model predictive control. With that we will kind of finish this more advanced topics in process control. Now, so as I said before, I am going to add more details to this block diagram, and you have to remember that if you are adding more details to a block diagram, you should have more information that can be used by these details. So, if I do not have any more information than what I have in terms of just a control variable and an output, there is no point in expanding this diagram, because the expansion has to be in response to some extra information that we have. And let me explain what I mean by that here. In the previous picture, we had both of this together as GP. Okay. So, let me take an example of how this works. So, let us take simple flow example. I am going to draw a very simple chart or a picture here to kind of look at a flow control loop and then explain what we mean by this GP and how I can break this down into smaller blocks or distinct blocks, and then talk about how I can use these this notion of this distinct blocks in controlling certain systems better. Okay. So, that is what we will get to in the next slide. For now, if you assume that there is some more information that allows me to break this G of P into this GP1 and GP2, and I can use that information to better the control. I am trying to see how I can add more structure to this closed loop, so that the control becomes better. So, now what I have done here is I have done nothing other than simply rewriting the closed loop transfer functions by simply replacing GP by GP1 times GP2. That is all I have done. So, in the previous slide I have GPCS divided by 1 plus GPCS and GD by 1 plus GPCS. Now, that GP I have replaced it by GP1 GP2. So, I am saying that process block itself I can write it as a multiplication of 2 blocks. Okay. So, when would this be useful and when would this happen? So, the idea is the following. Let us take a flow process. Now, if you are looking at controlling a flow out of a pipe, so I am just going to draw a rough diagram here for you to understand the basic idea behind what we are talking about here. The valve design and so on itself is little more sophisticated, and there are different types of valves that you can use and so on, but this is just to give you an idea of how this flow control occurs, and then what it means when I use only one block for this and what it means when I use 2 blocks for this. So, if I think about a flow control, okay, so I have this pipe, let us say I am looking at the flow out of here. The flow control is done by usually using what is called a control valve, okay, and the control valve, let us say something like this, and then so when you kind of move this up and down, the amount of constriction that comes about in this pipe changes. So, if you pull this out completely, you will have complete flow. If you pull this in completely, you will completely shut down the flow, and depending on what location you have in terms of the stem, you are going to get different flow rates. That is how flow is controlled. Now, so when you have a controller, okay, so there is a controller here. So, let us do the controller here. So, what the controller does is it takes this value, there is an instrument, measurement instrument which measures this flow value, and then it is going to cut a flow set point that you are interested in maintaining, and then it sees the difference, and then based on the difference it gives a control action. So, the control action, again like I said, this is just to illustrate this and make you understand in the simplest possible way. The actual mechanisms could be different based on the different configurations. You can think of this as basically applying a force on this or relaxing a force on this, so that the stem moves up and down, right. So, if you want 0 flow, then you have to apply enough force so that the stem goes down and completely blocks the pipe. If you want complete full flow, then you completely relax this flow so that this goes up all the way out. Okay. So, basically the controller output is kind of you might think of it as a force that is given to this system, and for it to push the stem up or down so that the flow is regulated or controlled. So, this is your standard. Now, if you think about this, then this I can think of together, because there is a stem that is moving and there is a dynamics with respect to the stem moving itself. So, basically there are 2 things that are happening that you want to notice. Number 1 is the amount of block based on the stem position, right. So, I have a particular stem position, okay, which is either down or up and so on. Based on this stem position, there is a flow that is fixed. So, supposing I am, let us say I am at this stem position, and then I go to this stem position. So, there is a flow rate that you expect when the stem position is here, more blocked, less blocked, those are the two flow rates, but as soon as I move from here to here, the flow does not change immediately. So, there is a dynamics that is associated with this. So, whenever the stem goes from here to here, maybe the flow has to increase from here to here, but there will be a dynamics which will be associated with this. Okay. So, this is what is called the flow dynamics. Okay. Now, also notice that when I apply a force here, so the force, if I apply a certain force, let us say the stem position is this, and if I apply certain other force, the stem position is this. So, when I go from this force to this force, it does not mean the stem will go from this position to this position immediately. There will be some dynamics between that force and the stem position, right. So, it will take a certain amount of time once I change the force for the stem to move. So, when you think about this whole loop and you think about the controller, the error between the y set point and y is driving the process in terms of a force, right, which is applied on the stem, and before you see a change in the flow rate in response to a control action, there are two different dynamics that operate. The first dynamics is actually the force to the stem position, which is called the valve dynamics, and the second is the stem position to the actual flow that comes out of the pipe. Okay. So, there are these two dynamics, and clearly once you apply a force, then the dynamics has to take into account and push the stem down to a particular position, and then once that position is reached, then the flow has to react to the change in the stem position, and then the flow will change. So, both the dynamics are important, and typically you will have this valve dynamics precede the flow dynamics, and in general if you do not even measure anything here in terms of where the stem is and so on, then the only information you have is the force you apply and the flow you see here. Okay. The fact that the force is applied, a stem moves, and based on the position of the stem the flow changes and so on, while it happens you have no information about that. So, that is the reason why what we typically do is we have only a GP, and we basically assume that we do not know what is happening internally, but we do an experiment where let us say I change the flow, change the force and see how the flow changes, and based on this change we come up with a dynamic model which basically directly relates the force that you exert to the flow that you see. So, that GP will subsume both the valve dynamics and the flow dynamics together. Okay. So, this is your standard system. Now, the difficulty with this is the following. So, now if we do not measure anything more, there is nothing more you can do, but one of the problems that you can notice right away is the following. So, typically let us assume the valve dynamics is much faster than the flow dynamics. So, let us say you want a certain flow, which basically means that I have to move the stem to a certain position, and remember I said no model is perfect. So, I cannot exactly know what a stem position is, right. The model will predict if you are here and there is a certain flow, and if you go here there will be certain other flow, that is just a prediction. So, what flow you will exactly get here will be slightly different, that depends on the true process transfer function and so on. So, the key idea being, if you want to get a particular flow here, basically let us say you give a force, and then the only way in which where you can figure out whether you have got the required flow is by looking at this flow rate. And if this is very slow dynamics, then what will happen is it will take you long time before you figure out that you should have moved your stem little more and so on. Okay. So, in some sense what will happen is you cannot speed up the process anymore unless you bring in some more measurement. Okay. So, basically you have to see a change here before you make a change here and you get to a stem position. But now let us say there is some problem with this part here, the stem was supposed to go somewhere, but it actually did not go there. That again you cannot infer any other way other than by seeing the flow change, right. So, the flow did not change as much, then you will go back and put this force, more force or less force, and then the stem will move, and whether the stem has gone to the right position and so on, we will only figure out after we measure the flow. So, in other words, I am restricted by the dynamics of both the valve and flow in terms of how fast I can do this control, and in some cases might be not happy with the closed loop performance you get when you simply make all your judgments for what force to apply based on flow, which is at the last step, right. So, the question is, if I am unhappy with the performance, in other words, if I keep increasing my gain till it becomes unstable, that restricts the performance I get, and I look at the performance and then say this performance is still not good enough for me to work with. So, is there some way in which I can change the performance or make my closed loop even faster? So, currently there is no way of doing it, but if you add more information, okay. So, what does that more information mean? Supposing you said, okay, I am also going to make a measurement of this stem position. Okay. So, I have a force, then I actually measure where the stem has gone to. Okay. Now, there is a way in which I can add more details to this closed loop to make this better. So, this idea of adding more detail through this and cascading the controller instead of just one controller is the notion of cascade controller. So, here the idea is the following. So, what we are going to do is, if I do not measure the stem position, I do not have a measurement here, in which case I just put one GP here, which is a combination of the valve dynamics and flow dynamics, and I cannot do anything other than the standard closed loop. Supposing I have a measurement here, okay. Now, remember my closed loop transfer function is GPC by 1 plus GPC, and this GP is, I told you, GP1 GP2, which is in this case the valve dynamics times the flow dynamics. Okay. So, if I do not have any measurement here, basically this is the best performance I can get. So, and since this is the best performance I can get, I have actually designed a controller for this best performance. Now, the question is, if I want to improve my performance, I am not happy with it, what can I do? Somehow I have to change the GP. Okay. So, the minute you have to change a process transfer function in this case, then you have to do some measurement, some hardware change, otherwise you cannot do this. In cascade control, you do this in a particular way. So, I am going to show you what the cascade control is, and please watch how this GP will change, and I will have some handle over what the GP itself is after I do the cascade control. So, conceptually what this really means is that now I am unhappy with the performance GPC by 1 plus GPC after I have found the best controller that is possible. So, if I want to improve the closed loop performance, I cannot do anything more to the controller, because for this GP I have found the optimal solution. So, the only way in which I can improve the performance is actually changing GP itself. So, I should have some knob or a tuning way of changing GP. How do I get that is what cascade controller does. And if you want to change the process transfer function, and this is the kind of idea that comes up in more advanced control, where if you have your standard design and then you design a controller and you are not happy with that controller performance, then the only way in which you can improve the controller performance is through what we call as redesign. So, you can redesign the process, or in this case we can redesign certain aspects of the process by adding little more hardware and measurement. So, any time you redesign the process, basically you are either adding subtract hardware and also adding more measurement. So, the whole field of how do you do this design changes so that your system becomes more controllable is a much more advanced idea and control, but cascade control gives brief and a very interesting look into this idea, while being very relevant from a practical application. There are many cascade control structures in industry. Okay. So, basically what you are going to do now is, you remember in the last slide I said GP1 and GP2, if there is no measurement in the middle, then I cannot do anything. I have to simply measure this and then go back and compare it with the set point. But if I add a measurement here, okay, which is basically in the valve case a stem position. So, basically there is a force, there is a stem position. In the first case I did not measure that, I only measured the outlet flow rate and then saw how the force affects the outlet flow rate. But if I actually measured a stem position, then what you can do is you can give a set point to the stem position and introduce another controller, so that this controller basically looks at the set point between the stem position, and now since I have a measurement, I can compare that measurement against the set point and then close the loop inside. Okay. So, there is one inside loop and another loop outside, and this inside loop is possible only if I am able to measure the output of the valve dynamics, which is the actual position, right. So, now if I am able to do this, then what I can say is, let me introduce another controller C2 here, and then this becomes the inside loop and there is an outside loop which was already there. So, this is what is a cascade controller. There is the inner which cascades to an outer, and if you look at this block diagram compared to the one before, there are two controllers that we have, and in the previous case this GP1 measurement out of this y went with the y set point, and the controller said what should be the force that you should keep. Now, this controller is going to do something different. What this is going to say is, this is going to say, instead of what force that should be kept, it is going to say what is the stem position that should be kept. So, it becomes a set point to the secondary or inner loop, and once this position is measured, that position is checked against whatever is a set point, and then now this controller will use that information to say what force should be kept here, so that the position is maintained. So, the force comes here. In the previous case only I had GP, the force came right after C1, but the force comes after C2, whereas C1 gives a set point to this internal controller, internal closed loop, which is to say what should be the stem position. So, that is the basic physical idea of this cascade controller. So, the outer or the master controller, whatever you want to call it, gives a set point to the secondary or inner or a slave controller. So, now we have this. So, what happens now in terms of analyzing the transfer function? So, what I am going to do is I am going to show you this idea that, okay, so how do I come back to my original simple block diagram? So, the idea is the following. Remember, in one of the previous lectures I said, okay, so if you take this part, okay, at this point and this point, this is where some new structure has been introduced, some new complication has come in. So, what I want to do is, if I want to come back to my standard structure of how these control loops look, then basically what I want to find out is, I want to find out what is the transfer function between this point and this point. Then what I can do is, I can simply put that transfer function block here and then make it look like my standard closed loop block. And I have already said, if you have a closed loop, if you want to find the transfer function between any 2 points within this closed loop, then you go from here to here, multiply all the blocks that come in the forward path. In this case, the blocks that come in the forward path are C2 and GP2, and then the denominator is 1 plus all the blocks that take part in the loop. And if you go through this loop, the transfer functions that take part in this loop are only C2 and GP2. So, this will be 1 plus CP2 GP2. So, this whole substructure within this, I can replace it by C2 GP2 divided by 1 plus C2 GP2, which is what you see in this diagram. So, C1 still remains, GP1 still remains, and now it has become C2 GP2 divided by 1 plus C2 GP2. Now, what did we gain by all of this? Okay, so, if you ask that question and say, okay, we did all of this, what is that we have gained? Notice something very interesting that has happened here. I started by saying that if I did not do this measurement and so on, I am going to, so I said if I were not going to do any measurement and so on, basically I said the closed loop transfer function is going to be GP2 GP1 times C1 divided by 1 plus GP2 GP1 times C1, and then GP2 and GP1 are known. I have found the best controller for this, and I am still not happy with the closed loop performance. What do I do? Okay, so, this is basically originally was GP. Now, what we have done is, now this GP, because I got that extra measurement, has been converted to GP1 times. So, now initially what was GP was GP2 GP1. Now, because of the cascade controller, this GP has become C2 GP2 divided by 1 plus C2 GP2 GP1. Okay. So, we started by saying when I have this GPC by 1 plus GPC and I found the best controller and still I am unhappy with the performance, then the only thing that I can do is change GP. So, initially GP was GP2 GP1. Now notice how I have been able to change this GP to C2 GP2 divided by 1 plus C2 GP2 GP1. So in other words, the desire that I expressed was that I should have some tuning knob to modify the process transfer function. Now if I think of this as the overall process transfer function, at least a part of it now I have a tuning knob to modify, so that this overall thing will be different from here. Okay. So by doing the cascade control, I have somehow inserted a tuning knob so that I change my process transfer function itself, so that I get performance that is desirable, right. So instead of just living with GP1 GP2 C divided by 1 plus GP2 GP1 C as my performance, now because I am able to modify GP2 itself with a tuning knob that I have, I can actually tune this to get better performance. So in the previous case, once I have the best controller, I cannot do anything more. Now what I can do is, since I have changed the process itself, that gives me first better control, and for this process I can look at another controller which will give me a performance that is acceptable to me. So that is a beautiful idea of cascade control in terms of how you modify the process transfer function itself, but to modify the process transfer function you have to add more measurements and add more hardware to be able to do this. Okay. So now once you have this diagram, it is very simple. Usually what you do is the inner loop, that is here, you first tune, and this you tune using a simple P controller, because it is fast, it is efficient. And also remember, ultimately there is another controller outside. So if you put a PI controller here, you can get rid of offsets and so on. So you do not have to really worry about offsets in the controller inside. The only criterion that we are looking for is that the controller could be fast. So typical P controller is good enough for the inside controller. So once you design the inside controller, then you can actually compute this. Now your transfer function becomes C2 GP2 by 1 plus C2 GP2 times GP1. This model for this you know, model for this you know, this is a controller you have defined yourself, which is just a constant. Now for this process, now you could use any technique to design a controller. You could use a Ziegler-Nichols tuning, you could use Cohen-Kuhn tuning and so on, or a direct synthesis approach to design this controller on this modified transfer function. Okay. So the first controller is a simple P controller, make it fast, and once you do that, you have this modified transfer function model, which again you can use everything that we have learned in terms of controller design. So you can either use Ziegler-Nichols, Cohen-Kuhn, IMC based tuning, or you can do some direct synthesis form that you are interested in, and then you can tune the outer controller. What this would do in terms of physical system is, if the inside dynamics, the valve dynamics is a particular rate without closing the inside loop, by closing the inside loop, what we are doing is we are making the valve dynamics faster, right, because the typical idea of a controller is to make sure that your closed loop dynamics is faster than your open loop dynamics. If I did not do a measurement of the stem position and then close the loop, I have to live with the normal valve dynamics, but because I do a measurement of the stem and close the loop, I can now have valve dynamics which is faster than normal, which will help with the overall control of the system. Now if you really make it really fast, that the minute I have a set point for stem position, I go there, clearly the dynamics is then only dictated by the stem to the flow, and that we are not doing anything about. We are only minimizing the effect of this valve dynamics by making that faster from a closed loop viewpoint in this case. So notice how by adding a measurement and thinking about this in terms of tuning knobs for modifying the performance of the control loop, we are able to come up with this control structure called cascade control, and also see how using the same rule where between 2 points, if I want a transfer function, I take the forward path and then do this 1 by 1 plus all the transfer functions in the loop as a way to reduce the transfer function between 2 points which has a substructure into one block, and then we put that into the same structure that we are comfortable with, and then once we get to this structure, then GP is just a multiplication of this 2, and everything that we have learned till now can be used in tuning this controller. So, this is the basic idea of cascade control, and as I said before, this cascade control is used quite a bit in process industries, so that you can get performance that is really acceptable from the viewpoint of your objectives for control. So, this is the first time we have seen how to add substructures to this loop. Another way of adding substructure using feed forward control is something that I will talk about in the next lecture. Thank you.